In this lecture, we're going to introduce and talk about the main type of relaxation, or dual bound, that we're going to use. And that's going to be a linear programming relaxation. Here we have some integer program. And this integer program's feasible region is a set of lattice points. The idea behind an LP relaxation is that we're going to take this feasible region, which we can call, say, X, and replace it with this alternative feasible region that's a polyhedron. And the polyhedron here is going to be defined, and let's call this polyhedron P. This polyhedron is going to be defined by the linear constraints that are defining our integer program region. The difference between these two is that whereas the integer program is going to be defined over lattice points, the LP relaxation is going to have no such lattice points. In practice, to create a linear programming relaxation is really rather simple. Let's suppose that we have some integer program, and let's suppose that it's a binary integer program, so that x's are either 0 or 1. To make a linear programming relaxation out of this, all we have to do is relax the integrality constraint. The integrality constraint here is that x's have to lie in some generic lattice points. To make the linear programming relaxation, we just say that the objective value is going to be the same, the linear constraints are going to be identical, but now x's are going to be less than or equal to 1 and greater than or equal to 0. This is in general how we make a linear programming relaxation. We take the integrality constraints and we replace them with the same copy of the x's lying within some real band, real numbers. In this case, because x's are either 0 or 1, x can be any real number between 0 and 1. For other integer programs, where x's can take on different values, we have to relax the x in the appropriate way and give it the appropriate bounds. To really understand a linear programming relaxation, we should understand it geometrically. Here we have our integer program with the optimal solution z star. And we can see that this is going to be a maximum over all the x's inside of some lattice points, capital X. Our linear program is going to be a maximum over some points, but this time the points are a polyhedron. The points in X are going to be the polyhedron intersected with some generic set of lattice points. In this case, the generic set of lattice points is going to be the natural numbers. If we were to look at this geometrically, what we're going to have is our linear programming relaxation is going to be this polyhedron that's going to encircle the lattice points defined by X. In this case, this polyhedron, this pink guy, is going to encircle all of these blue points, which are defining X. This is the geometry behind a linear programming relaxation. There's some set of lattice points, and by relaxing the integrality constraint, replacing the constraint that it has to be an integer, a natural number, or 0, 1, with the constraint that x's can be any real number, we circle all the lattice points in our original integer program. One very nice property of linear programming relaxations is that there's a close connection between the quality of a relaxation and all of the things that we've talked about in polyhedrons. Specifically, we can talk about ideal formulations and how ideal formulations relate to linear programming relaxations. Let's suppose that we have some polyhedron P, and P is ideal. Remember the definition. If P is ideal, that means that P is going to be the convex hull of the points X. So in this case, if we have our points X, these blue guys, our polyhedron P that I'm about to draw in pink is going to be the convex hull of these blue, which means that I'm going to effectively connect the dots on the outside of these blue points. This is an ideal formulation. And we can see why an ideal formulation is going to be so useful to us. If we have an ideal formulation, and we have some objective function, in this case f of x, then the optimal solution of our linear programming relaxation is going to be the same as the optimal solution to our integer program. So by having an ideal formulation, we can relax our integer program to a linear program and recover the same optimal solution. Let's reinforce this point. This means that if we have z star, which is the maximum over the points x in capital X, that is the points in the lattice point, on these lattice points. And this is going to be the same as taking this maximum over all the x in our polyhedron. And taking the max over this polyhedron is our linear programming relaxation. ZLP is easy to find. We can do this relatively efficiently, whereas Z star might be hard. Whenever we have an ideal formulation, we now know that finding Z star is going to be easy. We can use even more of the power of these polyhedron properties that we talked about earlier. Specifically, we can talk about good versus bad formulations. So let's suppose that we have some integer program defined on the points x, and here we have x, the points x drawn in our lattice. And now we have two potential polyhedrons, P in pink and P in green. Our pink polyhedron is a strict subset of the green polyhedron. So we can draw our pink polyhedron. Let's say it looks like this. And we can also draw our green polyhedron. Our green polyhedron is going to contain all of the points in X, all these blue points, but it's also going to be a strict superset of the points in the pink P. Now we can directly equate these two different formulations, or these two different polyhedrons, the pink and the green one, with the quality of the relaxation. In this case, we have an objective function f of x, and the polyhedron, this green one, is going to have some objective value that's quite high. The pink polyhedron is going to have an objective value that's a little bit lower. And both of the polyhedrons are going to have objective values that are larger than the true objective value of our integer program, drawn on this blue line. We can label what these are. This is Z star, the optimal solution to our integer program. This pink guy we'll call Z upper bar 1. This is the upper bound achieved by the pink polyhedron. And this green guy we can call Z upper bound 2. The relationship between these polyhedrons and one containing the other is directly related to the quality of the upper bound that they give. Specifically, if we look at the distance between Z star and Z1 upper bar, this is going to be less than the distance between our optimal solution Z star and Z upper bar 2. Because this distance is larger for the larger polyhedron, we're going to call it a worse formulation. It's a worse formulation because it gives a lower quality upper bound. That is, although its objective value is higher, that's a bad thing because in this case, higher objective value means larger distance away from the optimal solution.